So, yeah, I think, yeah, so the student T, I already explained that student T is able to, you know, because it has like a heavy tail, so it's able to, you know, give less importance to points that are, you know, the outlier points. Okay, so this one interesting thing is if you look at the values for you know, the summary of the this trace. Okay, if you look at the alpha, beta, epsilon, v. Okay, something you may feel a little bit strange is that, okay, you see standard deviation is 0. Okay, actually they are not 0. It just means like it's so small because we when we print it out, I mean, we only output like the first few digits. So, you know, the standard deviation is really small. I mean, this can be observed from, for example, like the range of the HPD. Remember, this range of HPD represents like HPD 94%, right? So it's from, you see, the alpha range from 7.11 to 7.12. And the beta range from like 0.34 to 0.35. And epsilon range from 0.00 to 0.01. So they are very, very highly concentrated. Oh, the only thing we didn't show is that the V underscore, the you know, the one that we use for the to shift the V, right? But that one is not you know, it's not directly it's not of direct interest anyway. So just want you to be aware. Okay, I mean, you know, the value alpha, beta, epsilon are very, very narrowly defined, and even more so is epsilon. Actually, not only epsilon, but alpha, beta, they are all very narrowly defined. Okay, and they're like standard deviations are all 0. Okay, close to 0. That means not using that 0 here is problematic. So this is totally reasonable because given that we are fitting a line to a perfect aligned set of points. Okay, because as I told you, like this data set is very special. It's, by the way, this is like intentionally created to show you if your model is not robust enough, it's going to be affected by the outlier. Okay, but if your model is robust enough, okay, then it actually can, you know, disregard outlier and create a much better, you know, prediction. Okay. So, so if you run a posterior predictive check to explore like the how where, okay, model capture the data. I mean, well, you use like the PPC. Okay, we do this. I mean, the posterior predictive sample posterior predictive to generate the sample. I mean, we do this. I mean, so many times. So this is, you can see that. Okay, if you still remember, this black line is the distribution of the Y value. Okay, and because this posterior predictive check is to use to generate the Y. Okay, and we use that to draw the you know, the kernel function. Okay, I mean the generated Y value looks are here. Okay, you know, I mean it's indicated by the very light blue lines. Okay, they are posterior predictive result, and their kernel line, okay, result looks like here. Okay, so it's reasonable representation of the data, except this one, of course. But this one is because of the outlier. Okay, so it tells you like this model actually ignored the outlier, you know, which is reasonable. Okay, for this particular example. Okay, so yeah, I guess that's about it. And then previously we talked about the hierarchical model, and obviously the hierarchical model also work for linear regression. Okay, so the hierarchical model, to create a hierarchical model, obviously we need to include hyperpriors. Okay, and this is like the idea. This is the code to create like A data groups. Okay, this A data groups. I mean, we draw it on the next slide. Okay, the first 7 groups are not so much interesting. The one that is interesting is the last group, which contains only 1 point. Okay, so remember, like in the hierarchical model, I think we talked about that like at the end of last chapter, right? And we talked about several advantage of hierarchical model. Now I would like to show you another advantage. Okay, so here, okay, if you try to generate one model for each group, okay, without hierarchical model, okay, this is pretty much standard. So I will, I will not go into like detail of this. This is, we use this like several times already. Okay, it's just basic linear regression. But one interesting thing is like this. After you generate, the samples, you generate a posterior distribution. Okay, and then when you look at the alpha and beta, remember, for linear regression, the most important thing is the intercept and the slope, right? But when you look at the intercept slope, you will find that, well, for example, alpha 0, beta 0 indicate the intercept and the slope for the first group. Alpha 1 and beta 1 indicate intercept and slope for the second group, and so on. Okay, so you can see that all the other groups looks okay, but group 7, the one with one single point, okay, show extreme wide range of the 94% posterior predictive, the HPC. Okay, same thing here. Okay, the range is very wide for the slope. It's so wide that you don't even see the range, of the other group. Okay, because the range for the last group is too wide. So because you can see like this is from -150 to +200. This is like the scale is so big. Okay. So what's the problem? It's actually very simple. What we are doing is we are generating a linear function for a bunch of data points, right? Right? So here, okay, if you have this data points, okay, for the first group, you can imagine, I mean, you can draw a line somewhere around here, right? Okay, for each group, you can sort of come up with a reasonable line, right? But the last one, how do you come up with a reasonable line? To have a line, you need to have at least 2 points, right? Right? If you have only 1 point, how can you have a line? I mean, it could be, it could go, of course you can have a line that go through this point, but you can imagine like it could be just like that Wheel of Fortune thing, right? It could range like the intercept and slope for that line could range like widely, right? So that's like the issue. But well, that's the result of one single point, right? That's the result of the data. Okay, so what do we do? Okay, what do we do? I mean, there are pretty much 2 ways to deal with this type of issue. The first one is you have a stronger prior. Okay, I mean, assuming you know some background knowledge about these data points, and you can specify those information in your prior, and by doing so, like I mean, your posterior, okay, obviously the data is not enough to confine the posterior, okay, but the prior can be used. Okay, remember, like a posterior is controlled by the prior and the data or likelihood. So if the likelihood is not strong enough, I mean, you could use the stronger prior. Okay, but if you don't know that either, okay, but at least if you know these A groups comes from the same organization, say like you are collecting water sample from 8 different districts that are under the same government, for example. Okay, so if that's like the data has a hierarchical nature, then what happens is that you can create this hyperprior. Okay, this hyperprior, okay, is shared by all the groups. Okay, and then okay, with this model, I mean, obviously this is a hierarchical model. Okay, the data point from the other groups can be used to provide like a better estimate of the hyperprior, which in turn will help you to restrict the posterior of the last group. Okay, because as I said, I mean, if you don't know the prior for that group, but at least you can use this one to indirectly restrict the prior, I mean, of the last group. Okay, so this is like this is the code. Okay, the code is basically direct like translation of this model. So I think it's pretty straightforward. So I will not go into the detail, but just want you guys to know that, okay, by using this approach, you don't need to have a strong prior. You don't need to have a strong prior, and you just try to get the information, okay, from the other group, okay, to help you to restrict the posterior of the last group. Okay, so you can see that, okay, by using this, okay, eventually, well, you can see that, okay, the range, okay, is much narrower. Okay, you may wonder, well, it looks like it's still range very widely. That's because, I mean, the scale is totally different. Now it's from, you see the scale from 0 to 6. The previous is from 150 to 200, right? Okay, so it's like more than one scale difference, right? And because like the range is much narrower, okay, for the last group, okay, so you can see that the other group, you can see their range now. Originally, because the scale is so big, so the other groups, that their range collapse into one single point, okay? But now, you can see that, I mean, obviously because the other groups, because they have more data, so their range are still narrower than the last group, okay? Because you can see the other groups, like, you know, each one has maybe like 10 to 20 points, right? Obviously, only the last one has 1 point. So I mean, the posterior, of course, is affected, okay? In the hierarchical model, the posterior is affected by, by both the hyperprior and the data itself. So here, okay, yeah, the last group, I mean, because it doesn't really have a lot of data, but I mean, it's only affected by the hyperprior, okay, that which is restricted by the data point of the other group. So in some sense, like, I mean, yeah, I mean, it's restricted, but it's not, it's still not like, you know, confined as much as the other groups. So that's why, I mean, you can see that the resulting, you know, this range, the last group, the range is still the widest. And in terms of the slope, again, this one is much wider, which is reasonable. Okay, which is reasonable. Okay, so so a good way to compare model is to show the parameters of both model. Okay, yeah, I think today, I think I will just, today I'm going just to stop here today, okay, because I'm really tired, okay. First, I mean, yeah, yesterday, I mean, I wasn't able to sleep at all, like, because of the thing, had a dinner appointment, and we drank too much, and yeah, so I think I will stop here, and but I think we are ahead of my expectation, because like we have let me check. This is the slide. Yeah, we actually went through like about 50 slides today. Okay, with this pace, I think like we need another 1 and 1.5 lectures to finish this chapter, and then, as I said, I'm going to go back to the MCMC. Did I give away the MCMC slide? If not, I'll have to, you know, have the TA upload the slide. No? Okay. So this is the last slide I gave out. Is that right? Okay. Okay. So I will have the some new slides uploaded. Okay. So I guess that's about it. I mean, we are about, well, 15 minutes earlier than to stop today's lecture. I'm sorry about that, because I'm really exhausted. Okay, so Any question? If no question, I mean, let's just call it a day. And yeah, as I said, I will post the final project, okay, sometime before the next lecture, and also should be after the next lecture. I'm going to post like homework 3, and along with homework 3, you need to find your teammates, and it's going to be 3. Each team will have 3 members. So please find your teammate. If you couldn't find your teammate, okay, at the end, the TA will assign the teammate randomly for you. Okay, I don't think this is a good idea. Okay, it is. I have seen examples in the past, like some teammates never show up. Okay, and if you don't want that to happen, I really suggest that you find your own teammate. Okay, even though I know like a lot of students, they just don't show up at all in the class. Keep in mind, like eventually in the presentation, you guys need to come, right? Okay, you guys need to come to the lecture. Otherwise, I mean, how do you do the presentation? So even if you don't know, you don't see your classmate, but at least I believe you know somebody who take this class, right? Supposedly, okay. Unless you really cannot find anyone, talk to a TA, and maybe we can try to help. But if you don't do that, okay, we will just assign random, the random teammates for you. Okay? Yeah, so that's it. Thank you.